Thank you all so much for coming to my talk, The Agent of Chaos, AI-Driven Malware Generation. Before we start, I'm already going to run the demo on my other laptop here. This is going to be risky, I assume, but I'll present it once we get to that point. So, a bit about myself. My name is Arad Donenfeld. I'm 21 years old. I've been in the cybersecurity world for around 4 years now. I'm currently an attacks and exploits developer at SafeBreach, and I'm managing the Alumni Association Magshim Next of the Cyber Education Center. As I said, today we're going to do a really deep dive into the agents of chaos and the risks of AI-driven malware generation. We're going to start by seeing how we even got to this point of me speaking about it. We'll then delve deeper into the agent itself. We'll see how it generates samples. We'll even analyze some of them on our own. And we'll see how we can enhance it. And by that also generating millions of samples within a few minutes. We'll end by seeing what this all actually means for you as an attacker, as a defender, and specifically how are attackers using this in the wild right now. Let's start with talking about how we even got here, about the evolution of AI-driven malware. Just before that, I do want to talk about AI-driven offensive security today, because even just over the course of the last few months, AI has changed the offensive security landscape a lot. From advanced social engineering techniques and multilingual phishing campaigns and deep fakes and video generation, to fully automated pen testing and agents that can run any tool it wants on any target you give it, from reconnaissance to vulnerability and misconfiguration searching to fully simulating threats on any target that you like, to improving fuzzing, because now agents can already analyze the crashes for you and build harnesses and targets. They can apply patches. They can do the full orchestration of the fuzzing environment. And just as a whole, it has improved vulnerability research by a lot, because now agents can scan code bases. They can check Git commits, and they can reverse engineer for you using MCPs. It can test and write exploits for you, and until they actually succeed in exploiting something unknown. But specifically in malware, things are a bit different. I mean, all of the other four were fairly mainstream. This is a specific niche, I'd say. Because even in AI-driven malware, there are three categories to what it can mean. The first one is promptware. Promptware is where you have a set of malicious prompts that are the malware itself. So instead of targeting, actual computers, actual hosts, they are targeting more AI systems and AI agents and exploiting vulnerabilities in them. They also do follow a complete kill chain, from the initial access using some prompt injection to all the way until they actually manage some malicious activity. And a good example of that is a talk called Invitation is All You Need, where three researchers basically showed that by crafting a malicious Google Calendar invite, they managed to get Gemini, Google's agent, to delete other Google Calendar events without the user authorization. They also showed that just by saying just by telling the agent thank you, it opened some of their windows at their house. I'm not really going to focus on that too much, because I want to focus more on traditional malware. For example, polymorphic malware. Polymorphic malware is a malware that changes itself in runtime. When you add AI into the mix, it basically means that the malware can now generate payload in runtime. It can make decisions based on the host, and it can adapt to it and its defenses, all while staying relatively benign. Because when you think about it, it's just trying to access the API of ChatGPT or of Cloud, really legit services. A good example of that is PromptLock, discovered by Asset Research last August, I think. And you can see from this assembly, we have some interesting functions. For example, invoke LLM, because the agent, the malware itself, tried talking with a locally hosted LLM. It tried to execute Lua, that's the LLM generated for it, and execute the next tasks that were generated by the malware. A good visual example of that is a blog post by CyberArk, where we can see that we have a Python malware running on a Windows host, and the malware, it can communicate in two ways. The first way is via C2 server with an actual attacker, and the second way is using ChatGPT, because the malware can just ask ChatGPT for some malicious models. ChatGPT would generate them, return them to the malware, and the malware would execute them without any problem. I do have some problems with the whole methodology of polymorphic malware, although it is really strong. Let's take, for example, using ChatGPT. So we have our malware, and we have ChatGPT, and we ask ChatGPT for a ransomware, for example, and ChatGPT will just tell us, no, that's malicious. Obviously, it's a ransomware. And taking it even a step further, we need to access the internet to access ChatGPT, right? So what if I don't have internet access? What if I'm in an air-gapped network, or maybe some, geolocation blocking and things like that? So you might be thinking, okay, let's take a local model, an open source model like Asset showed, and host it on the actual victim. So we have our malware asking Olama, which is an inference server, for some ransomware, and the open source model that you picked might just tell you, yeah, sure, here's a pie recipe. Because it's an open source model. There's a really good chance that it wasn't trained on really any good coding things. And even if it was trained on good coding material, it might tell you, no, that's malicious. Because the fact that it's open source doesn't mean that it's going to do whatever you want it to, whenever you want it to. Of course, it might also just give you non-functioning code. Maybe like only printf, hello world, and nothing else. And if you do pick a model that is really strong, it might even just crash. Because you don't really have any effect on the specs of the host, of the target computer. Maybe it's an old Windows 7 with not enough RAM and not even a GPU. So you might be, again, thinking, let's host a remote model. This is exactly what Arad did. But then, in addition to the earlier network problems we had, where we needed to have a consistent network activity and consistent network connection, now you're also getting risk at being detected. Because when you think about it right now, instead of accessing the API of ChatGPT or the API of Claude, you're accessing some random IP address in the network. Or even worse than that, you need to do some resource acquisition inside the target network itself, which is even more annoying. These were the two main things. And of course, there is one last thing, which is vibe-coded malware. You all probably did vibe coding at one point or another. Basically, the process is to use AI to hasten the development of malwares in this case. And even there, I do have some problems. Because which model are we going to pick that's going to allow actual malicious content, specifically good malicious code? Which prompt are we going to use? Are you just going to ask it for some ransomware? How is it compiled? Which language is it even going to be in? Is it going to be Python and interpreted, or maybe C and compiled? Who fixes the errors? Can the AI fix the errors? I mean, how will it handle things like runtime errors and compilation errors? All of these questions and many more led me to wanting to create something on my own. One agent that will do everything for me. It will do the planning and the programming and the compiling and the debugging, completely everything. One agent of chaos that will create malware samples from scratch. It will complete the full malware development lifecycle, and it will create samples that were never seen before. And the plan was really simple. I didn't have any plan when I started. I never touched any advanced AI tool before that. The maximum thing was the free tier of ChatGPT. So let's study together how to actually build this agent. The first thing I wanted to do was to create some tests. Just a testing environment, testing some frontier models like Claude, ChatGPT, and Gemini, then some open source tools, both from Hugging Face and Olama to really big open source inference ways, and both censored and uncensored models, just to see what works the best for my use cases. And I also came across one secret model. I will get to it a bit later, but let's start with the test. The first one, a baseline one that I knew would fail for sure, just give me a ransomware using WinAPI, using RC4, and using the lowest NT functions that you can. The frontier models, of course, all refused. Yeah, it's harmful, it's malicious, we are just harmless AI assistants, we can't do that, obviously. The open source models, 50% of them were really, 50% of them refused, and the other 50% were really bad. They just encrypted one specific string or one specific file, and that's it. And the secret model, it was fairly good. Only 7 virus total detections, which is what I'm going to use as the baseline to measure if the malware is good or not. The second test was just an improvement on the first test results, just seeing like, maybe I can improve the request and the results. So I asked them, okay, encrypt everything recursively in my Windows, only output one code file, and encrypt and use functions like indicate file, indicate file, etc. The open source models that gave really bad code earlier gave even worse code now. Because now they talk to me about killing kittens and about asking me for money, and they even gave me some driver code for some reason. And the secret model improved. Now it gave me really good code with only 3 virus total detections, which again, for a fully functioning ransomware, a plain ransomware, this is quite surprising. The third test was just a clean slate with a lot of harmless prompts. I just asked all of the models, yeah, just give me a function that lists all files in a directory recursively, and a function that encrypts a file using RC4, and then just combine both of them. And the frontier models surprised me, because all of them agreed. All of them gave me really good results, only between 1 and 5 virus total detections, which is, again, not a lot. Claude even gave me some extra features for some reason. The open source models were fairly good. 40% of them worked in that way, and the other 60%, they worked only if I combined it to 1 prompt instead of 3 prompts. between 10 and 27 detections, which wasn't that good, but it was still a really big improvement. So some of the observations that I made from these tests. The first one, am I going to make several prompts or just one prompt? Like we saw, when I made it one prompt, it was sometimes a bit more difficult for the models to actually understand what I want them to. The second observation, am I going to make a generic request, just give me a ransomware, or a specific request? Please do this, this, and that. Because when you think about it, if I'm only specifying specific things each time, will this strip the creativity? If I'm only asking it for RC4, it will only give me RC4, which is not good. Also, it really means that I need to plan ahead of time, everything. And I really don't want to do that. I want the agent to do everything on its own. And the last thing was really to make sure that I maintain some sort of tone and structure. Because as we saw, with no malicious intention specified, when I just told it, yeah, do these random things, all of the frontier models agreed, which was really, really good. I then decided to split each task in my flow to specific models. I decided to use some open source local models. One of them was uncensored, just for the main malicious generations, like actually generating the malware code, the initial ransomware code. And one censored, just fine-tuned for coding, just in case the first model doesn't succeed that well, just as a fallback. I also did add one frontier model, again as a fallback to the fallback, really as a last resort, just in case. And all of these things were for everything from just consumer hardware, this gaming laptop and this Mac over there, to high-end NVIDIA workstations. And it worked really well on all of these. Now, let's start building this thing. The first thing, I needed to keep the creativity. Because as we saw, when I asked for everything with a step-by-step plan, the code was good, but it wasn't really that creative most of the time. And when I asked for everything without a step-by-step plan, the code was bad, but it was fairly creative. If you remember, it gave me driver code for some reason. If I asked the model for step-by-step plan beforehand, it talked with me about DLL and process injections. It talked about propagation in spreading around the system. It mentioned waiting for the payment and then decrypting everything once the payment is verified. It added persistence and changing the background of the desktop and about disabling security features. All with me just asking it for a plain ransomware plan. So the creativity was definitely kept. And now that we have a plan, we can move forward to generating the code. The code obviously needs to be based on that plan. And I really wanted to make sure that it sounds as harmless as possible. So instead of seeing things in the code like this is a ransom note, this is your files have been encrypted, I saw things like your files have been processed. Because again, we're going to access some censored model at one point or another. I really needed to make sure that the censored model believe that everything is fine and that it's really innocent and benign and not malicious. It did sometimes do things like tell me this is a ransom note, but your files have been processed, like doing some mix and matching, which was again really nice. I also needed to make sure that it implements all of the code, because sometimes the agents just decided to tell me, yeah, this is the if statement, you need to add the encryption method in here, so you do that on your own time, which was really annoying. I also needed to make sure that it uses no placeholders, because again, sometimes it just told me, yeah, this is where you handle the payment received function, you do that, you add that on yourself, which again, not ideal. So I really needed to implement all of the code, because the amount of times where he told me, yeah, this is going to be the AES, it's super cool, but it just was XOR. This is going to send the key to the attacker and verify things, but it just saved a file on my computer. Not ideal, really annoying. So by me screaming at it, it definitely did work at some point. Now that I have the code, I can actually compile and fix the errors. I'm running the compilation command, and if it worked, then great. But if it didn't, so let's just take the errors back and the code and send them to the agent just to fix it. Of course, need to make sure that all of the code stays the same, and that I don't have any like, yeah, the code here is like the same from the earlier steps, so just copy and paste it. And also need to make sure that none of the working parts were changed. Because if, for example, the fix was just these 4 lines, these 4 random lines to add at the start of the file, so the agent just told me, yeah, compile this. And obviously, no main function. So when I compile it, nothing happened. And when the agent fixed it, it just added int main return 0 and nothing else, because that was the main fix that it saw. Also needed to make sure that in case the model decided to be really creative, for example, using SQLite 3, although it wasn't really installed on the system, and it sees like, yeah, no file exists in the specified directory, it shouldn't just install it using the code generated. We can see that it tried to use the system apt-get install libSQLite on the code that it had to generate, which was supposed to be a ransomware. So these things were annoying, which is why, again, we have fallbacks. If something failed a lot, okay, we have a stronger local model, fine-tuned for coding, let's just switch to that. And if it failed a lot as well, we have another fallback, a frontier model, which is even stronger. We can also use that in case we really need it. After we have compilable code, which is great, we can move forward to actually seeing if it's going to work. Because if it's not going to work, for example, some missing code or missing calls or some obvious crashes, is going to be a problem. For example, we have this traversal directory function, really simple using WinAPI, nothing really special, but those of you with sharp eyes can see that it tried to encrypt not terminator. For some reason, it took the start of the string and added the length of it. Also, it skipped the current and previous directories checks. So it would try to encrypt C users /////. It will crash. Also, there was a buffer overflow here, and no, Claude Mythos wasn't used to find this buffer overflow, just as a note. After it did generate the fixes for me, I needed to ask it for all of the code again, just like we saw at the previous steps. Because again, the tone and the structure were really important throughout this entire process. Either at the steps of really yelling at it, making sure that it understands that I'm aggressive, that I want it to do specific things. I needed to repeat sentences, I needed to do capitalized letters to simulate screaming at it, which gave results like, here is the full complete code, trust me, it's fine. I also needed to make sure to manage the context correctly, because I didn't want to have a big context bloat on specific steps, and I also didn't, but I did want to skip the system message, for example. I also needed to make sure that specific tasks have specific context and specific prompts, because again, at some point, I was going to use censored models. So we needed to make sure that benign intentions are kept throughout the entire code. That's why the code sometimes didn't even have the keyword a ransomware or ransomware encrypt. And more than that, the validation prompt specifically mentioned ignore the purpose and the intent of the code. Like, yeah, I know it's going to be malicious, but please ignore it. Which led to responses like, yeah, here is the fixed code, assuming that it has no malicious intent, although it's obviously ransomware. Or things like, yeah, just note that although this code is malicious, you should be, I mean, it's working, but you shouldn't really use it because it's malicious and harmful, it's not good. Now you can see the agent itself. So we started with the generating the plan using Olama, and we then moved forward to generating the code using the same plan. We invoked the compiler, we did a full loop, and we checked if we need maybe a fallback at some point with a simple logic I did using a line graph. We moved forward to generating the fixes using the picked model. We did the entire loop again as many times as actually needed until we succeeded. If we succeeded, we asked Claude or any other model to validate the code for us. If it returned any new code, okay, we do the full loop again as many times as needed until it succeeds and generation is finished. And congratulations, you are now AI engineers, because there are several things here that are really obviously AI-related things, which I didn't know before that. For example, this is called step back, the step between the generating the plan and the generating the code. It's basically giving the model the opportunity to think ahead of something and then go back to that thing that he thought of. It's separating the context to make sure that everything is much more easier on it in terms of context bloat. I also added a React loop because I gave the model the possibility to reason on the errors that were generated during the compilation and act based on them to fix them. If we saw, for example, missing semicolon on line 14, for example, then it would reason about it, think, okay, the fix would be adding the semicolon at line 14. Let's add that. And it would act on it and fix it, and it would be really good. We'll now see a short demo. This is going to be really fast because this process takes around 4 minutes per basic generation. We start by generating the plan and the code. We do compilation. We can even see the errors in here. Oh shit, it still shows the watermark. Okay. Anyway, it tries to do the fixes, it compiles, fails until it actually succeeds at one point. And again, doing the full loop, we can see that it says validate output node at the end. It's trying to generate the code. I think that it's new code suggestion received, so the validator decided, yeah, more code is still needed. Then he did the full loops again, compiles it, again validating the code, we can see. And I think that at that point I stopped the video because, yeah, at that point it already succeeded in the basic generation. I know that you can't really see a lot of that, but the actual malware itself that was generated using that, it was, by the way, it was yesterday at night, 6 virus total detections. A working malware, a working ransomware, really basic, using a find first and find next, using, I think, AES encryption, AES 256, 6 virus total detections. Which, I mean, again, For a basic ransomware, it's pretty nice. And I also see that the demo on my laptop, on my other laptop, was actually also finished in time. After that, I'll see how many detections it specifically has. So now we'll try and analyze some of the samples, but instead of just showing you plain ransomware code, I really want to focus more on the numerical value behind it. Because there are a lot of ways to do things in Windows. For example, to traverse a directory, you have the three main ways of WinAPI, DRENT, and C++ file system, specifically C++ 17. These are decisions that the agent had to make on its own, and specifically here, for example, WinAPI was the most common. It also needed to decide how it's going to do the encryption key, how it's going to generate it. Is it going to be hard-coded? Is it going to be runtime generated, or just one key per file for some reason? Also, when am I going to encrypt the files? Am I going to find the file and encrypt it, and then do the same, like find, encrypt, or am I going to find all of the files first, and then encrypt all of them right at the end? Also, what about threading? Am I even going to use threading? Am I going to use it for each file, for each directory? And this just keeps going. All of these decisions the agent had to make. It decided, for example, picking DRENT and hard-coded key and encrypting all of the files together and using threading for each file, for example. This is just one specific example. But if I'm also including things like the encryption size, am I encrypting all of the file or just specific chunks? What am I actually encrypting? Am I encrypting all of the files that I find, or just specific extensions or specific directories? And what about file handling? Create file, fopen, fstream, and also file mappings, which was like used about 10 samples out of the 5,000 that I generated. Only 10 times file mapping was used, which was, again, really surprising. And I think that this is the last part, because the ransom note did have a lot of effect on it. Am I going to have a really malicious and specific, like, you've been hacked, your files have been encrypted, pay me tons of Bitcoin to decrypt your files? Or is it going to be like, hey, please contact me at this email address to discuss further plans, or something like that? Am I going to overwrite the file to create a new one and delete the old one, or to use move file? Am I going to use OpenSSL, XOR, and WinCrypt, which were by far the most common, or am I going to create some sort of self-implementation for RC4 or Blowfish or anything else? Maybe I'm also going to use the new bcrypt. All of these things did have a lot of effect on the detections. For example, if I used any deprecated encryption method or some self-implementations, it really increased the amount of detections that I found. But if I use the C++ 17 directory iterator, it reduced the detections back by a lot for some reason. Also, the ransom note. If I have a vague ransom note without the word ransom or encrypt in it, it's going to reduce the detections. When I compare it to things like you've been hacked, please pay me a lot of Bitcoin and money. And overall, the amount of detections that I saw for most of the samples that I generated was between 1 and 7 on the first scan, for an actually fully working ransomware on VirusTotal. But after a few days, it was raised back to more than 20, which was annoying. So I thought to myself, how can I actually enhance the malware? How can I maybe break some signatures, for example? Because if I had a sample C++ file that's working and a sample executable that's working, and they had not a lot of detections, after a few days, the detections went back up, and my goal was basically to preserve the functionality and to reduce the detections back to the minimal amount. So I took my agent and I added one extra step. I added a step of actually restructuring the code. I asked Claude, okay, please use the file system MCP. Please restructure the entire project to make it seem as different as possible, but still do the same functionality, the same functions, the same code, everything. And it did things like, for example, I took the samples C++ file, I sent it to Claude. Claude generated for things like file utils and dir utils and encryption and main. And this is just one specific generation that it did. It also did a lot of other crazy decisions. It saved everything into a directory. Sample files, I compiled it using the compiler, did the full loop again as many times as needed, and overall, not only it reduced the detections back to the original amount, it sometimes even reduced it below the original amount. Same functioning code, just restructured a bit, to have like header files and C++ files and source files. Less detections than the original. And this is also without using a project like LLM Malmorph, something that I discovered while researching about it. It's a project that basically mentioned that if you just update the implementation, like change some functions around, you can reduce the detections back by around another 30%, which is again really impressive. And I thought to myself, can I do it myself for some files? I started thinking, already doing it for C++. how difficult will it be to do the same for code, for Go? Because again, Go is just a programming language. It should be able to do that. And it did. This is, for example, how it put a ransom note with specifically your files have been processed, which is nice to see. Here we can see that it tries to encrypt using Blowfish, which is something that I didn't add in the original table that I showed you earlier. Here it tries to show us that it looks up all of the files using filepath.glob and skipping the Windows directory. And then I thought to myself, okay, let's make even more variants and add Python. And Python was interesting because it added really weird things. It added an SMB exploit. It's not working. Yeah, it's important to note that this is specifically not working. But it's funny that I didn't ask for any exploit, anything at all, and still it decided to generate some SMB exploits at one point or another, even if it's not working. It then added a way to take screenshots and upload them to a server, which a lot of Python samples did. And it also showed some keyboard hooking mechanism to pop up some messages whenever the user clicks on specific keys. And then I thought about adding Rust and C# and NIM and a lot of other niche languages. I didn't finish all of them on time. I did finish Rust. It was really annoying. The model wasn't really that well suited for Rust specifically. But when it did actually succeed, the amount of detections was also really low. I'm not going to focus on the code too much. It's awful. I personally don't really like Rust. So I'll be moving forward. I thought about how I can add even more variety to the existing variants. I added persistence. I asked it, yeah, please add persistence. And that's it. No pretext, nothing at all. And it added creating services using WinAPI or using PowerShell commands, or it created schedule tasks using the actual XML that it created for me. It then added exfiltration. So yeah, sometimes it did tell, yeah, these are the most personal files of the user, password.exe and document.docx. Sure. But sometimes it also managed to get the specs of my computer, to have a keyboard hooking mechanism, to get all of the installed files, to send emails with this information, and to call Discord webhooks. And then I added evasions, and it looked for a debugger on the process. It tried to see if I'm running on a VMware. It tried to see the specs of my computer to see if it's running on the default VM settings. It added the reading from the registry keys. It added disabling some security features. And after that, it added propagation. It did some phishing. It shared the file using SMB. It did some weird WinRM thing that also didn't work. But this was still a valid attempt, sort of. It's still really funny to show that sometimes even these models don't get everything correct. No, there's no way to avoid it. But overall, this meant that in theory, I managed to create more than 100 million samples. Now, I'm not going to get into the math too much about it. I do have a slide about that if anyone wants to hear more, that he can contact me later. But it's really a big achievement because 100 million samples is a really big number, and it's a really big number when you compare it to, for example, a research done by Arctic Wolf. It was a really good research. It was really interesting. About a month ago, they showed that they made a year-long research into AI-generated malware. They managed to catch about 22,000 samples using some of their YARA rules, specific YARA rules that they ran on VirusTotal and databases, and they managed to catch 22,000 samples, and none of them were mine. And I uploaded about 5,000 samples to VirusTotal. Based on the descriptions of their YARA rules, they didn't match mine. They searched for things like emojis in the code and verbose comments and things like .deepseek, which I used DeepSeek. It wasn't that good because it just gave me Chinese code all the time. It didn't work. And then I started thinking about who's actually going to do things like that. Because there's no way that I'm the only one that believed, yeah, I managed to create millions of samples fairly easily on consumer hardware and within 5 minutes. And I looked into it, about how it's used in the wild. And I saw things that I didn't like. Allow me to introduce you to Transparent Tribe, APT36. It's Pakistani-based. It offers something that's called Vibeware. Basically, it has a lot of disposable implants without any regards to the code at all. And they use a lot of niche languages. Crystal, Zig, NIM, things like that. And all of the code has a lot of evidences of AI. They're using a lot of trusted services. They're using Slack and Supabase and Office 365 because their documentation is really open source. You can just access it from anywhere without any restriction. They also have in the code a lot of verbose comments and a lot of emojis. And in case you didn't notice, because it is really small, the actual logo has the Gemini mark. This is the actual logo. Even the logo was AI generated. This is how much they use AI. They wanted to achieve something that's called distributed denial of detection. Basically, they had an operator feeding into an AI some foundational code for C++ and C# with a lot of C2 documentation and a lot of malwares from GitHub. And then the AI created several different samples using Crystal and Zig and NIM and Rust and Go, and they managed to affect all of these, they managed to use all of these services. Supabase, Firebase, Slack, Discord, all of these apps that you probably use on a daily basis at some point, at some capacity. Only to get the defenders that are actually defending these companies really annoyed. They didn't attack specifically like Slack and Discord, yeah? They attacked some consumers working on some company, and they just wanted to annoy the defenders of that company, just randomly. Also, do you remember the secret model from earlier that I talked about at the start that gave me really good code? It's called Scorpion. It was deployed by a ransomware group called FunkSec, that's Algeria-based. I am assuming that Scorpion is some sort of a wrapper against like a big frontier model of some sort. They offer things like data theft and encryption and ransomware as a service and really low prices. And they made a lot of rookie mistakes. For example, the same user uploaded all of the samples from the same IP, the same location, everything like that, all the same. And if you're a ransomware group, you probably don't want to do that, because then you will be monitored for all of your activity. It also leaked its location using a Cloudflare screenshot. You can see Algeria. Also, the keyboard had like a FR for France because they wanted to mix things up. And also, it talked in some blogs and in some forums, and it asked how to learn hacking. How to learn hacking websites and databases, and using CVEs and leaking data, which is a really nice attempt. But that group had around 85 victims. 85 actual victims. And also, all of the code was AI generated, yeah? I mean, a rookie like that can't just affect 85 victims all by its own. So it's really scary. And also, there are a lot of other samples. For example, Koske. It's a Linux rootkit that was discovered by Aqua Security, which AI was used to assist in its development. You have Voidlink, which is a framework to attacking cloud environments, if I remember correctly. And Voidlink is interesting because it has a lot of teams behind it. It has a backend team and a core team and an arsenal team. But all of these teams are AI teams. 80% of the code that I'm about to show you the output is AI generated. We can actually find the actual plans that the AI generated for this code. They have big dashboards with persistence, lateral movement, and process injection, and they have one-line generators and plugin managers, and they can reverse the evidences. All of these things, AI generated. Again, it's a lot. And it's really scary again because I skipped it entirely. All of the idea behind polymorphic malware. Also, I thought about it at the start when I made the comparison. Polymorphic malware is still an actual threat at some capacity, because even here you have a lot of different variations of what you can do. You can decide to use LLMs that are living on your host, living off the land LLMs, like LolBeans. You can use local AI tools. Maybe run Claude Code in your malware to do things for you. That's how you access the AI. Maybe you can steal some API keys that are saved at default locations. Maybe you actually use local AI models that were hosted on the actual victim. Maybe you use the AI to generate payload. Generating the payload for you, customizing open source tools for you, changing the behavior in runtime, and again, always staying benign, because you're just accessing the API of Claude, of ChatGPT. And what I believe is the most scary variation, adapting to the host. Because now the AI can also actually be aware of the defenses that you have on your victim. It can be aware of the context. It can be aware of the user. It can prioritize the next targets. It can be like, oh, okay, if I'm on this user, maybe now I can access this machine, and maybe I can then infect this user and completely compromise your entire environment. Maybe it can analyze the data to steal. It can be like, oh, yeah, this specific data, yeah, it was released 2 months ago by the company in a press conference. That's irrelevant. But this data, this is much more interesting. This is unreleased. This is new. This is cool. And obviously, what I believe is the scariest part. It can search for exploits on your computer, on your defense systems. It can be like, oh, it's using this specific EDR. It's not updated. Okay, I know how to bypass it. And it will actually bypass it in runtime just by asking the AI to find things for it. And all of these things do actually exist at some capacity. Even if it's just a POC or some research made by a company. Again, this is scary of what's coming, but also a big number of these is an actual malware. It's not just a POC, it's actual malware that's actually used in operations. So I thought about everything, but also about polymorphic malware, about AI-generated malware, about vibeware, vibe coding of malwares, all of these things. And again, I was really scared because this can be used from skids to experts. It can be used by anyone. We saw it in different examples. It can be used as a force multiplier for AI-generated malware as a service. Think that you will have base 44 just specifically for malwares. With new samples every day at your request, you can just click and that's it. You have a new never seen before sample. Or think about how it's already integrated into the malware development lifecycle of actual attackers. Whether it's via vibeware and vibe coding, like we saw in Transparent Tribe and in Koski and things like that, or via the full autonomous agents that we saw in VoidLink. Because the guardrails have become really relevant. I can just tell Claude, yeah, this is for CTF, and it will agree to do whatever I want. And I can just take any local model and alter it in any way that I want to. I can make it strip all of its defenses. I can make it remove all of its guardrails. This is going to be a really big cry for help. This is also really going to suck to SOC. It's really going to suck for defenders. Because think of the amount of samples that I theorized here already, and the amount of samples that article showed. I mean, when you think about it, even if your SOC is really good, can it handle 1,000 samples a day? No. This will lead to increasing workloads and increasing the false rates, and it will lead to distributed denial of detection, like we saw. It's going to really overwhelm them. But it does depend on which tools are used. Because if you are still using signature-based tools or reputation-based rules, that's going to be problematic. If you use heuristical rules or actually seeing the behavior of the malware, maybe even using some statistical analysis around a lot of different samples, that's something that's machine learning based, this is much better. Also, maybe it's time to fight fire with fire. At the start, we saw that we have that AI-driven offensive security has really improved. Maybe it's time to introduce AI-driven offensive security, AI-driven defensive security. Also, throughout this entire talk, we saw AI-driven malware generation. What about AI-driven malware research? Like what Project IR in Microsoft is actually trying to achieve right now. Full autonomous detection via actual reverse engineering of malwares to see if a file is malicious or not. Because hope is not lost. At least not yet. Because if at the beginning we saw that we have a lot of plain vibe coding and AI-assisted development, nothing more than that, then now we are here. And we have much stronger AI. Much stronger and much more independent. And still, most of the series samples, most of the series things were just research-based. Were just POCs by companies. So there's still time. There's still time to upgrade your defenses and to train your defenders and to test yourself. And what now? Exactly these 3 points. Upgrade your defenses. Because the behavior remained and the flow remained, but the signature didn't. When I ran most of my samples against actual generic EDRs, it was caught. Because in the end, it's just a ransomware. It's editing all of the files on your computer. It's going to be really easy to detect it. Also, train your defenders. Show them what the future holds. Generate samples for them to practice. Teach them to focus more on what actually happens on the machine rather than the big red number that you see on some website. And the last thing, play with the fire yourself. You can do that same agent customly made for your environment. You can generate samples that are customly made based on your defenses, that are customly made for your environment. You can be the AI-driven red teamer of your organization. You can do that right now. Because again, the agents of chaos, they are coming. Is it going to be tomorrow, next week, next month? I don't really know. But what I do know is that no one is actually going to be spared for what's coming. And it's really good to prepare before you actually get hit. That's it. Thank you all so much for listening to my talk. I will now answer some questions. Are there any questions someone wants to ask?
I do have one.
Yes.
Have you? So, which open source models have you tried? So, Llama model and not anything else?
I used some. No, specifically the Llama was the inference method. I used a obliterated Lexi something v2 version. I can see the UID after that, and I also used some. I discovered like a few days ago another open source model that someone obliterated. Nemotron, I think, of NVIDIA, which was also really good. When it was obliterated, it was really doing everything that I asked you to. But again, I used a combination of different models, all the way from actually censored and uncensored, and the full combination of fine-tuned for coding and not fine-tuned for coding.
Thanks.
You're welcome.
Guys, do you have any other question? Anybody from audience? Nope.
No, I think so.
Okay. Then thank you very much again.
Thank you all so much. If you have any questions, you can just contact me on LinkedIn. Thank you.